Okay, so we're going to be going over note 10 from CS70. This one is about counting. So we're going to start off by talking about counting sequences. So specifically when we're counting sequences, we want to make sure that we're keeping track of the order of these sequences. And there's a couple of rules that they define in this note, and I'm just going to sort of go over them using examples. So, basically we're going to count the number of ways of picking 52 cards from a deck, right? So if you think about a set of 52 items, you can pick one card out, right? Now you have 51 cards. And from those 51 cards, you can pick any one of those 51 cards. Okay, so say you pick a second one. Now you have 50 cards, and from any one of those, you can pick, one out of that. So basically, if you want to find the possibility of removing K cards, then you would just say, for the first one, you have 52 options. For the second one, you have 51, all the way until 52 minus K minus 1. Okay, so this is sort of a generalization of this example. So basically N1, there's N1 ways to make the first choice, and then for every way of making the first choice, there are N2 ways of making the second choice, and for every way of making the first and second choice, there are N3 ways of making the third choice. Okay, and you can think of this sort of as a tree too. Let's see. So there's a distinct number of objects. So let's see. Yeah, the number of leaves. So, yeah, as we can see, there's 12 here, because at the first level we can make 2 decisions, and then for each of those 2 decisions we can make 2 more decisions, and for each of those 2 more decisions we can make 3 decisions. So 2 times 2 times 3 is 12, which is how we calculate the number of decisions. Okay, now we're going to go on to counting sets. So the difference now is that a set, remember, is a unique collection of elements, right? For example, the set 1, 2, 3 is equivalent to the set 2, 1, 3 or 3, 2, 1, etc. So let's see. So say we want to find the total number of ways of picking distinct sets of 5 cards each from a deck of 52 cards. So as we know from the above equation, it's going to be 52 factorial over 47 factorial. Again, 52 factorial is the number of ways to get all of the possible cards, and then 47 factorial is basically we're just dividing out everything, because if we think about what 52 factorial, it's say K is like 3, right? So we want 52 factorial times 51 factorial times 50 factorial, and that means we would have to subtract out 49 factorial. I believe I did that right. Yeah, so think of this but in terms of 5 cards now. So how do we calculate the number of distinct sets? So note that a set of 5 elements has 5 factorial distinct permutations, and I'm going to illustrate this for a set of 3 elements. So let us switch over to Paint. So let's think about a set with 3 elements, and okay. Wait, let me just make sure. Yes, okay. Alright, so let's say our set is just 1, 2, and 3. At the first level, we have 3 choices, so we can choose 1, 2, or 3. Say 1, 2, or 3. And then from there, we have 2 choices. If we pick 1, then we can pick 2 or 3. If we pick 2, then we can pick 1 or 3. And if we pick 3, then we can pick 1 or 2. And then from there, we have from there we just have one more choice. So it's kind of like that. So if we have 1 and 2 in our set, then the only other element we can add is 3. If we have 1, 3, then the only other element is 2. I'm just going to kind of fill in the rest. 2, 1. And if you notice, as per the above tree illustration, all of these leaf nodes here, the sum of them is the number of possibilities that we have in terms of basically permutations of this set. And what that looks like is 3 factorial. Right, because at the first level we have 3 decisions, at the second level we have 2 decisions, and at the last level we have 1 decision. So that's 3 times 2 times 1. Okay. I'm going to switch back to the LeetCode window. Okay, let's see. Okay, so that just kind of illustrates how a set of size k can take on k factorial distinct or k factorial sequences. So since 5 factorial sequences are placed into each bin, yes, because that's basically what I just said. So a set is going to kind of be a bin, and then all sequences that fall into that bin must be a part of that set, if that makes sense. So again, this is the total number of sequences. If there are 5 factorial possible different bins, then this is just the equation that we're going to generate, which is n choose k. That's how you say that. So it's the number of sets of length k in set n. And k is a subset of n. So let's see. Yeah. Okay. Second rule of counting. Let's see. So yeah, I guess this is more of like a visualization. Again, I guess these rules are more like generalizations of specific things. But basically, we're gonna have the set A, which is a number of unique sequences, and B, which is a set of unique subsets. And basically, these unique sequences will map to certain subsets, where M is the... Did I finish this? M is the number of unique subsets, actually. No, sorry. So B is the number of unique subsets, but M is... Let me actually just double check this. Right, so the notes define M as... let me just put this down. I have caps lock on. Is the number of sequences per subset. So in this case, we are defining for ourselves that the number of sequences per subset is the same. So for example, let's say we have a sequence of 5 elements, and then we want all unique sequences that are, all unique subsets of size 3, okay? So like one subset could be 1, 2, 3. Another subset could be 2, 3, 4, for example, right? Both those subsets, 1, 2, 3, and 2, 3, 4, have 3 factorial possible permutations. So that's what it means when I say the number of sequences per subset is going to be the same for all subsets. And this is something that the second rule of counting relies on. Okay, so let's see. The quantity of ordered objects per unordered objects is the same for all unique sequences that fit into unique subsets. Every 5 card subset has 5 factorial possible orderings. Yeah, so that's basically what I just said. Okay, now we're going to move on to something called sampling with replacement. So basically, each time you pick an element out of the set, you put it back in before you pick the next one. Okay, so I guess it would be n to the n, just possible, or wait, forget I said that, or n to the k, or yeah, n to the k. So n to the k, where n is the size of the set and k is the number of times you sample. Yeah, okay. So what is card dealing an example of? Card dealing is an example of sampling without replacement, because as soon as we draw the card, it's not put back into the deck, right? So we're not replacing the card. Coin tosses, however, is an example of sampling with replacement, and we've seen something similar to this in note 0, this sort of tree-like structure, the way I illustrated it when we were talking about power sets. And I think we're going to see something about power sets later on in this note too. But, just to think about this, say we want to flip a coin 3 times, and we want to think about, what are all of the possible combinations of heads and tails that we can generate if we flip the coin 3 times, right? So we could get tails 3 times, we could get tails twice, and then a heads. And in this case, the order does matter because, let's see. As you can see, we get tails, tails, head, and head, tails, tails, but those are considered different. So we want the number of unique sequences of flipping a coin 3 times, or k times. So again, the very beginning, we flip a coin, there's 2 possibilities. Once those 2 possibilities have occurred, there's now 2 possibilities for each of those 2 possibilities, and so on. So we're just kind of using a bit string representation to represent the outcomes, where 0 is a tail and a 1 is a head. Okay, and then rolling a dice is like the same thing pretty much. There's 6 options, and let's say we roll it twice. So you can imagine a tree with 1 root and then 6 branches, and then for each of those 6 branches there's 6 more branches. So that's why there is a total of 36 possibilities. Okay, now we're going to go into sampling with replacement, but where order does not matter. So let's look at this through the lens of the fruit example that they talk about in the notes. So imagine we have infinite apples, bananas, and oranges. So our set is going to be consisting of the numbers 1, 2, and 3, corresponding to the above fruit. We want to know how many unique sets of k equal 5, or of 5, can you make, given that you can reuse fruit. So let's see. Why can't we apply the second rule of counting? Well, if we think about what power we have now that we can reuse elements, say we want to make a set of, so the set has to be of size 5, right? Say the set consists only of apples. So in that case, there would be 1 sequence that falls into that set, right? Because it would just be 5 ones. However, if we want to make all of the sequences that include 4 apples and 1 banana, then there are 5 sequences that fall into that subset of 4 apples and 1 banana. And this is going to be illustrated here. I mean, well, it's not really illustrated, but hopefully you can imagine. In order to kind of put this into terms of something that we know, we're going to use like this balls and bins metaphor. So again, we have 3 kind of, what would you call it? Well, yeah, so we have 3 fruit from which we can choose, and then we're going to make subsets of size 5. Or, sorry, they're sets of size 5. They're not going to be subsets. So basically what we're going to reduce this down to is 3 bins, where each bin is a different fruit, and then 5 balls, where each ball kind of represents a slot in that set that we are trying to build. And we're just going to disperse those 5 balls amongst the 3 bins. And we're going to represent it as this bit string where zeros represent balls and ones represent walls. Basically the separation between each bin. So in the first bin we have 2 balls, and then there's a separation, and then 2 more balls, separation, and then 1 more. And the number of balls is equal to K. But the number of walls between each bin is going to be equal to n minus 1. I feel like that's fairly straightforward, because there's, if you have 3 things next to each other, there's like 2 gaps between all of them. But anyways, so yeah, notice how order doesn't matter, because placing, like, say we place the first ball into here and then we place the second ball into here, the outcome of this string would be the same if we place the first ball in here and then the second ball in there. Okay, good. And then let's see. There's also no repetition, so once a ball is used, you can't use it again. And yeah, that's the size. So the problem now becomes, how many unique ways can I place k balls among n plus k minus 1 bins? And from there we can just generate an equation, which is n plus k minus 1 choose k, and we can just sub in our values for n and k to yield the result. And that kind of moves into the 0th rule of counting, which will sort of become more important later on, which is that if there is a bijection between set A and set B, there's just like a 1-to-1 correspondence between the inputs and outputs, there's an inverse, then the cardinality of A is equal to the cardinality of B. I'm not too sure about the validity of this, like, at least in relationship to counting problems. It's really like, I mean, at a super high level, it's if we see something that we have seen before, or say we have this new problem, if we can convert it into something that we have seen before, then like, let's do that, because we know how to solve what we've seen before, or at least we should. Now, personally, I don't really see the connection between this problem and representing it as this bit string right here. I feel like, or at least the way the notes were for me, it just kind of said that, we can represent this as this bit string with these bins and balls, but I don't really see like how there's a bijection between these two. If anyone knows, I'd really appreciate it if they could leave something in the comments or something like that. But for now, we're just going to move on to the next section. So this is about combinatorial proofs. And the first one we're going to go over is called binomial theorem, the binomial theorem. So basically we're saying for all n in the set of natural numbers, if we have these a plus b terms, I guess, factors, and we just multiply them out n times, then we're going to get something that is of this form. And while this didn't occupy much space in the notes, this took me quite a long time to understand, and even now I don't think I fully understand it, but we're just going to go over what this stands for. So again, a plus b to the n is really a plus b times a plus b, and you do that n times, right? So f1 through fn is going to represent all of these factors. So f1 would be the first a plus b, f2 would be the second a plus b, and so on. And you should notice how there are 2 to the n monomials created before we sum the terms when we multiply out the n-fold product. This is easiest to see when n is equal to 2. 2 to the 2 is 4. So we have this and multiply it out, we can clearly see that there are 4 terms here. And something that is important to note is that when we multiply out each of the monomials, each monomial will contribute only an a or a b. And this is evident in this example, I mean, if you think about FOIL, first, outer, inner, last, each factor is going to contribute one A or one B. So, factor 1, which, let's see, yeah. So for factor 1, the first factor contributed an A, the second factor contributed an A. For this monomial, the second monomial, factor 1 contributed an A, and factor 2 contributed a B, and so on. This one is just the easiest to see. You could do A plus B to the 3 to see a more fleshed out example. But as you can see from here, we can let K be the number of A's contributed and n minus K be the number of B's contributed. And we're going to sum up K starting to 0 all the way up to n. So if we start at 0 and we have this equation, that means that the first term I'm going to get is b squared, which checks out because it's there. Now where you start to see where this actually comes together is when K increments up to 1. Because when K increments up to 1, you have A to the 1 times B to the 2 minus 1. So basically you have A times B. However, you also have this n choose K factor. And in the n choose K of the initial, that's just, what is it? That would be 2 choose 2 minus 0 times 0, n minus K factorial times 0 factorial, which is 1. So yeah, basically this factorial cancels out when K is equal to 0. But once we get to K is equal to 1, we now have 2 choose 1, which is 2, which means that there are 2 times this A times B term, which is exactly what we have here. There are 2 of these A and B terms. And then once we get up to K is equal to 2, we're just going to get A squared. So we can see that this formula does in fact equal that. So yeah, okay. I'm just going to go on. So corollary 10.1, the significance of this is just to show how I guess, widely usable the binomial theorem is. If we wanted to prove this statement right here, we can simply just plug in A is equal to minus 1, B is equal to 1, and plug it into both sides, and we can easily get some numerical value. So now we're going to go over combinatorial identities. So the first one we're going to talk about is called the hockey stick identity. And yeah, so let's see. Give me 1 second. Okay, so we have this expression up here which says n choose K plus 1 is equal to n minus 1 choose K plus n minus 2 choose K. And let's see how this works. So the way we're going to explain this is by saying we're going to get a subset, we're going to call it X, and we're just going to say that the first value of X is going to be the smallest value in N. Okay? And that means we now have N minus 1 elements to choose from. So let's see, is it unique? Yeah. So once we have a subset, so let me see. Choose from. Yeah, so we're going to want to generate all of the subsets that have 1 as the smallest value, okay? That means we have n minus 1 values to choose from for every other value in that subset, leading up to K. And yeah, I'm not 100% sure of the validity of this statement, but I think it's right. And then we basically extrapolate that out. We say that if we choose the second smallest number, let's say 2, as our smallest number in our subset, which is of size k, then because we've already made all of the possible subsets with 1, now we're confined to a subset that has 2 as the first element, and then n minus 2 other numbers for the rest of that subset of size k. So yeah, and that process repeats until we choose the n minus kth element of our smallest value, and that's pretty much summed up by this picture right here. So another combinatorial identity, I guess, is this one. Now this one's a little more straightforward, at least for me. So this is where the power series comes in again. So if we think about what each of these terms is, basically what one of these terms is saying is that, n choose I is the number of subsets of size I that you can make from n, right? And if you think about what the power series is, it's all of the possible subsets of n, right? So I think they illustrate this pretty nicely. So say our set consists of these 3 numbers. All the possible subsets would be the 0 set, set with just 1, with just 2, and then 2 elements, and then 3 elements, right? There's also a bit string representation, which I don't know, they really like sliding bit string stuff in. It must be important, I guess. But as we can see, 3 choose 0 is just equal to the 0 set. 3 choose 1, how many unique subsets of size 1 can we generate? Well, that would be 1, 2, and 3. How many subsets of size 2 can we generate? That would be 1, 2, 1, 3, 2, 3. And then how many subsets of size 3 can we generate, given 3 elements? That's 1. And so this 1 plus 3 plus 3 plus 1 is equal to 8, which is also equal to 2 to the n. So again, I guess just for my sake, n choose k is how many subsets of size k can we create given n elements. Okay. So permutations and derangements. We're going to use this example of homework. So we have n students, and they each turn in, one piece of homework. So there's a total of n homeworks, I guess. Now we're going to shuffle all of their homeworks and then give them back to those n students, and we want to know what is the probability that they'll get their own homework. I don't think we actually go over the probability, but we're going to talk more about what this looks like in mathematical terms. So we're going to have a set S, which is going to represent all of the homeworks. So homework from student 1, homework from student 2, all the way up to homework from student n. Okay. Now we're going to have this set pi, where the ith element in pi is the homework that is returned to the ith element in S. And notice that it doesn't necessarily have to be the same homework, and that the size of pi is equal to the size of S, because pi is really just a set permutation of S, and therefore there are n factorial possible permutations of S. Okay, and if it is ever the case where a permutation of S has some point that is in the same position in S that it is in pi, then we call this a fixed point. So I think it's easier to see in here. Let's look at the second example. In the second example, there's one fixed point. Clearly it's 1, because 1 is in the first position, and then that means that there's 3 and 2. 3 fixed points, all of these are in their proper position. And here there's some examples of elements with 0 fixed points. None of them are in the right spot, or in the spot that they correspond to in S. And notice how you can't have 2 fixed points, because if you can't have 2 fixed points in a set of size 3, because if 2 of them are fixed, then that third one is left to just go to its own spot. Also, a permutation with no fixed points is a derangement. So these two examples right here are derangements. And it's not like really explained why, but we want to find the number of derangements of a given set. I guess that will help us in determining the probability, but I don't think we determine the probability. We're just sort of introducing concepts like surrounding this example. But anyways, we're going to notice that, and also even this is like slightly like loosey-goosey, at least for me, but say we have a set with 4 elements. These are going to be all of the possible derangements of those elements. So notice how no element is in the proper position. These blue numbers are a derangement of the set 1, 2, and then these red numbers correspond to a derangement of the set of n equals 3. And the way that they say that it maps to it is it's like, so we have the 2 derangements for n equals 3, right? These are the same 2 derangements here. Let me see. Yeah. These red numbers correspond to these numbers over here. I mean, I guess 2 and 1 are in the same place, and then the last value are in the same place. And the same for here, 2 or 1, and then the last values are in the same place. So basically we can create, we're going to say that there's like a relationship between those. There's a relationship between the derangement at n-1, which are these two, and a relationship with the derangement at n-2, which is represented by the blue. So that's going to segue into Theorem 10, which kind of involves both the derangement at n-1 and derangement at n-2. And just to say the whole thing, for an arbitrary positive integer n greater than or equal to 3, the number of d to the n derangements of 1 through n satisfies d sub n equals n-1 d sub n-1 plus d sub n-2. Alright, so how does this work? So again, our initial set has n elements in it. A derangement is going to be represented by pi 1 through pi n, where no elements in the derangement should line up with the element in S, as we've discussed. And that means that pi n, that nth element in the derangement, must be an element between 1 and n-1. Because by definition, it can't be the nth element, because then that wouldn't be a derangement. Okay, so yeah, there's n-1 choices for n, so I guess that's where the n-1 factor comes from. Again, I feel like they don't really explain it, but from there we have 2 cases, which also not too sure like why we have 2 cases, because I thought we defined okay, yeah. So for some other element in the derangement set, there's 2 cases. 1, it either equals n, or 2, it's just not equal to n. So if it is equal to n, then actually, yeah, no, that doesn't make sense to me. But anyways, we're gonna go with it. So if some term in the derangement set is equal to that last term, or let me see, give me 1 second. Okay, to be honest, I'm like very close to understanding it, but there's like something I'm missing, so I'm gonna go through it again. So n elements in the original set. Our derangement has some permutation of those elements such that no element in the permutation lines up with its corresponding element in S. Okay, and we're going to say that one of the elements in the derangement, the last element, has to be one of the numbers between 1 and n-1, because by definition it can't be n, because then it wouldn't be, a derangement. So we take one of those numbers between 1 and n minus 1, and now we're going to say the jth term in the set of derangements, it is possible that it's equal to n. Okay, and if that's the case, then we take the original set and we can swap the nth term and the jth term. And then with the rest of the elements, we have n minus 2 possible ways to create derangements. So basically, for the rest of the elements, we have d to the n minus 2. But it's also possible that for that jth element that's between 1 and n minus 1, that jth element is not n. So if it's not n, then there's n minus 1 remaining elements in the original set that we make a derangement with. Yeah, so it's just I'm stuck on like the swapping issue. Like, why do we swap j is equal to n? Let me pause. Anyways, I drew out an example. Here it is in Paint. Honestly, it's still not entirely clicking with me, but I sort of get it. Maybe, hopefully this will make it slightly clearer for you. It's not already clear. But anyways, we're going to move on. So basically this equation up here, where is it? I think it's no, it's not. Did we ever get, yeah, this equation right here. That corresponds to this equation right here, which we're actually going to derive later using the principle of inclusion and exclusion. So basically, inclusion-exclusion is a way of counting without overcounting. So let's say we have two sets, A1 and A2, which are subsets of A. If we want to get the size of all of the elements between in A and in A2, or A1 and A2, then we can just sum the cardinality of each of the sets, and then we have to subtract out any of the overlaps, right? So we're just going to generalize this to an arbitrary n number of subsets that are of the same finite set A. And this notation is fairly dense, but basically what this is saying is, I would look at the second thing. So we have n subsets of A, A1 through A2, A_n. We're going to union them, and we want to figure out the size of it, right? So basically what that takes the form of is we're going to just take the size of the A ith subset, subtract it by the size of the and of the A ith and A jths, and then we're going to add it to that sum of the sizes of the next three. So basically we're going to alternate multiplying and subtracting as dictated by this term, and then it's going to be just one subset, and then the intersection of two subsets, and the intersection of three, and the intersection of four, all the way up until n. And the proof, it brings like a lot of concepts together, and it's sort of hard to follow everything, but honestly the notation is not the hard part. It's just like keeping track of all of the different things and seeing how they fit together. But basically, if there's some element that is not in the union of all of those subsets, then that element is just not in one subset, and therefore if you were to AND a bunch of those subsets, it would not be in them either. And I'm not 100% sure if that's what this means, but I think it does. And we're going to create the set M, which is just going to be a bijection between so basically we have a subset. Yeah, okay, I'll just say this. So if there is an element in AI, then there's going to be a corresponding integer I in M. So basically we're just taking all of the elements in AI and boiling it down to just integer, an integer representation of each element. And that gives us this equation, which if we put everything together, we should be able to understand this, but I'm having a hard time putting everything together. So just to quote directly from the notes, the number of k element subsets of M is n choose k. I mean, that's fairly evident. And then, so what is it? The number of k element subsets of M. Okay, so this second sigma, so basically this statement corresponds to this side of the equality and this side of the equality. So the number of k element subsets of M just equals, you know, n choose k, or M choose, I think it's M choose k. Yeah, M choose k. And then, you know, that M choose k is equal to 1 if we follow the 10.1 corollary, which I have to sneeze, so I'm going to pause. Which is, again, if we use the binomial theorem and then we plug in certain values for a and b. But, I don't know. It's just I get all the parts, it's just I don't really get when they're all together. Again, we're going to try to use what we've learned to derive this equation right here, which is, you know, this up here. We just kind of said that this derangement is equal to this equation right here. So, I do not want to add a comment. Okay. So, let's see. Okay, now we're here. So, we're going to let the derangement of a set of numbers 1 through n, so we're going to have a derangement. It's just going to be the set of numbers 1 through n, okay? AI is going to be the set of all distinct permutations of d of n with I as a fixed point, okay? And note that there can be multiple fixed points in that permutation. We just need to guarantee that I is fixed. So clearly n factorial is the number of total possible permutations of the derangement, and the union of all of the distinct permutations of d of n with at least I as a fixed point, you know, all of those union together, we subtract that out of n factorial, we're going to get the derangement set. And we know that the cardinality of a subset, or, you know, all of all the distinct permutations of I, if I is equal to n minus 1 factorial, because, you know, 1 is that fixed point, or so I is a fixed point, and so there's n minus 1 other combinations, and then, you know, if we union these two, I feel like I don't know, I'm mixing things together. But if I and j are not the same, and we know that I maps to I and j maps to j, then there's n minus 2 other values left, which is yields these number of permutations. And then for any subset of size k, we have this, and then this is sort of where I get lost right here. Yeah, honestly, I'm not too sure how relevant this is going to be. We'll see. We might just have to use the equation, not necessarily know its derivation, but hopefully everything pretty much up to here has made some amount of sense. Again, this has been Note 10 in CS70, all about counting.